Part C is the white whale of a problem in Module 2. Part C is going to prevent you with every opportunity to make an algebra or arithmetic error. Because it's got fractions going on, so that's strike one. It's got the variable x on both sides of the equation. That's something we haven't seen yet, strike two. It also has mixed arithmetic. It not only has multiplications going on inside of this equation, but it also has subtraction. That's strike three. So this is the total package, this problem. If you can solve equations of this type, you are golden with solving equations until about mid-semester at least, right? So this is the Swiss Army knife of algebra problems. Let's see if we can figure out how to work it. So when you look at this equation, what's the first thing that you want to do to make this equation easier for us to get the x by itself? Based on the discussions we've already had, what do you think is a good first step to push the ball forward? What's the scariest thing about this equation? Everything. Well, so yeah, there's a lot going on, right? Three strikes. It's got mixed arithmetic, x's on both sides, and fractions. Of those three things, what's the easiest to take care of immediately? We could try getting the x's together, but both of our x's have fractions attached to them. We could try dealing with a mixed arithmetic, but that would require us to do arithmetic with fractions floating around in the mix. So the three things that make this a scary problem, I would argue, the easiest one to fix are the fractions. If we can make those go away, then we can focus on the other two problems, the x's on both sides and the mixed arithmetic. We can focus on those two independently and not have fractions still gnawing at us in the back of our heads the whole way around. Because that's what fractions do. And anytime there's a fraction still on the page, there's this little voice in the back of your head going, I don't know how to do this. Yeah? Tell me if I'm wrong. I don't think I'm wrong. So let's fix the fraction problem first. Based on the discussion we had about the problem in the middle, what do you think might be a way for us to fix that fraction problem? Step one. Exactly. Let's find the least common multiple, or really any common multiple, of the denominators in this problem. Multiply by it on both sides. That will wipe out our fractions. This is an underrated technique for algebra students, and I recommend it as often as I can. Clearing denominators is what we call it. Get some practice with this because it is going to be your friend. Any problem where we have fractions. And so we need to find a number which is a common multiple of what here? 3 and 5. I guess there's secretly a 1 in the denominator of that whole number 7 there, but 1 is not going to change what the least common multiple is when we throw it into the mix. So we really need something which is a least common multiple, LCM, of 3 and 5. What are some common multiples of 3 and 5? 15, also 30, also 45, also 60, et cetera, et cetera. So there's a whole lot of big common multiples of 3 and 5. Are there any smaller common multiples besides 15? No, that's the best we can do. That's because 3 and 5 have no common factors. Right? 4 and 6 had a common factor of 2, which made it so that we could get smaller than 24 for its LCM. 3 and 5 don't have any factors in common. They're distinct prime numbers. So the best we can do is 15. So what do we do with that 15? Just like in the last example, multiply, again on both sides of the equal sign, by 15. If I multiply absolutely everything in this equation by 15, I'm not going to have any fractions left. Everything is going to be a whole number. And from there, we can focus on the algebra rather than having to also focus on fractions at the same time. Which is why I like this technique. And so all of the fraction arithmetic that we have to do is now front-loaded. But luckily for us, all of it is multiplication. We don't have to add any fractions, we don't have to subtract any fractions, we don't have to divide any fractions. All we have to do in this technique with fractions is the easiest thing we can do with fractions, multiply them. So let's do each of the multiplications. How do I do 15 times negative 5/3? Okay, so first let's put that 15 with a denominator of 1. How about that negative sign? What should I do with that? We talked about this on Wednesday. I think it was Wednesday. When you deal with negativeness in a fraction, remember my recommendation is to always move it upstairs, put the negative sign in the numerator. Don't have negatives in the denominator to screw you up. So I'm just going to boost it up into the numerator. And then multiply across. Let's just say that. Let's multiply across. So 15 times negative 5, 1 times 3. And then we have to do negative 75 divided by 3. We know this is going to be a whole number because that's the way that this clearing denominators process always works. What is negative 75 divided by 3? 3/4 makes 75 cents, right? Negative 25. So that's one way of doing this fraction multiplication. Let me also suggest one more way. A slightly, I don't know if it's more efficient or what, but a different way to do that fraction multiplication. And I'm going to ask this by asking you first to think about what is the difference between, let's say, 15 times 5 and 5 times 15. 15 times 5 versus 5 times 15. What's the difference? We can reverse the order of any multiplication that we want to and still end up with the same answer. So how do I use that here to help us simplify these fractions? Well, instead of multiplying 15 by negative 5, what I'll do is flip-flop the 15 and the negative 5 first. So I'm going to just trade places with those two and bring the negative 5 over to the left and the 15 over to the right. And I'm going to argue that this actually makes our life a little bit easier in this problem. Because what's 15 divided by 3? 5. So I end up with negative 5 times 5, and I get that same negative 25 that we got before. But I like this because before we had to go all the way up to 75 in our product and then bring it back down by dividing it by 3. So we had to work with larger numbers in the middle of the process. Here, reversing my two numerators allowed me to keep the numbers smaller. When I had to actually do a division problem, my division problem was a simpler division problem to do than it was before. So make use of that. Some of you I know will have habits of doing things like cross-canceling and reducing and stuff like this when you're multiplying fractions. It's an equivalent process. This is just a different way of framing that. So however you do it, this fraction product ends up being negative 25. And so when we come back to this problem, we'll end up with negative 25x as the first term in this product on the left-hand side. Okay, but I need to multiply this same 15 by all the rest of my terms in this equation as well. This is another place where people make minor errors and end up losing the tune. Sometimes after all the work of multiplying 15 by negative 5/3, people forget to also multiply the 15 by the negative 7. So sometimes what I'll see is people will just sort of forget it and move on. Don't fall into that trap. If one thing gets multiplied by 15, so does everything else. So we have to multiply 15 times negative 7 as well. And unless I miss my guess, I think that comes out to minus 105. And then the same story happens on the right-hand side. 15 multiplying 4/5, 15 multiplying 1/5. When 15 multiplies 4/5, we can again flip-flop the 4 and the 15. So what we really have is 15 divided by 5 times 4. Which is going to give me a 12. I'll let you fill in those details on your own. And then 15 times 1/5, what's that going to give me? Same as 15 divided by 5. It's going to give me a 3. So we front load all the fraction arithmetic that we would have to do for this problem into this one step. So this one step might take you a little while to carry out all the multiplications and make sure that the multiplications are happening the way that they're supposed to. But after that step is over, all of your numbers are whole numbers. And once all of your numbers are whole numbers, we can focus on the rest of the process. We're trying to get x by itself, but we still have the same two problems we started with. We have an x on both sides of the equation, and we have mixed arithmetic. We have multiplication and subtraction happening in the same equation. So let's fix, now that we fixed the fraction problem, let's fix the both sides problem. How do we fix the fact that there is an x on both sides? What's your play? Because we need them all to be on one side in order to have x equals a number. Right? So how do we get the x's together on one side? Don't wait any longer than you need to move all the x's from one side of the equation to the other. And anytime you move a term with an x in it from one side to the other, it's a process of subtraction. I have a 12x on the right-hand side of this equation. If I don't want it to be there anymore, I need to subtract it. This is a subtraction sign. If I subtract it from the right side, I also have to subtract it from the left side. But when I subtract 12x from both sides, how many x's do I have left on the right? None. 0x. And in that case, we don't even need to write 0x anymore. It just becomes 0. So anytime you're fixing the x on both sides problem, the solution to that is always subtraction. Subtract to get the x's on both sides. How many x's do I end up with on the left here? Negative 25x minus 12x. Negative 37. We're taking a negative and we're subtracting. We're taking negative 25 and subtracting 12 from it, so it becomes even more negative. Gives us negative 37. I still have minus 105 over here. So now we've fixed the x on both sides problem. So the first problem we fixed was the fractions. We got rid of them by clearing denominators. The second problem we fixed was the x on both sides problem. We fixed that by subtracting one of the x terms from both sides in a way that it cancels on one side, as happened here. So now the last problem we have to fix is the mixed arithmetic problem. Because on the left-hand side, I've got multiplication going on between the negative 37 and the x, but I also have subtraction going on. I'm subtracting 105. So how are we going to get the x by itself? Which of those two operations should we focus on first? If I'm trying to get x by itself, what do you want to do? Here's how I like to think about it. The expression on the left-hand side of the equation, negative 37x minus 105. If I'm x in this equation, what's the first thing that's actually happening to me? If you were going to plug in a number for x and then evaluate this thing on the left-hand side, what's the first operation you'd have to deal with? Because why? Yeah, how do we know the multiplication happens first when you're evaluating an expression? That's the order of operations. That's PEMDAS, right? Multiplication happens and division happens before addition or subtraction happens. So if I'm x, the first thing that's happening to me is I'm getting multiplied by negative 37. And then only after that multiplication do I then have subtraction happening. So the way that the expression on the left-hand side is put together, it's like I've got an x in the middle of a box, and I've wrapped that box in a multiplication by negative 37. And then I've wrapped that whole box with subtraction by 105. But my job is to unwrap that box and get to the x that's in the middle. So if I'm going to unwrap that box, what's the first thing that I have to unwrap? Exactly. I have to unwrap this expression in the opposite order that it was wrapped. So if I want to get the x by itself, I have to undo first that which happened last. So when we're solving an equation to get a variable by itself, we don't use PEMDAS. We use SADMEP. We run the order of operations backwards because we have to undo first what was done last. So we focus first in solving an equation on any addition or subtraction that we can do to make the expressions simpler. How do I undo subtraction by 105? Add, exactly. So I'm going to unwrap this box by adding 105. I'm going to do that on the left side, and I'm going to do it on the right side. So negative 37x, 105 minus 3, 102. After I've added 105, I've taken care of all the addition and subtraction present in my equation. And only then should I think about the next innermost box. So now that I've unwrapped that much, now I still have multiplication by negative 37 on the left-hand side. And how do I undo multiplication by negative 37? Divide by negative 37. And again, don't forget that negative sign in your process. Divide by negative 37, and then I'm going to have an answer. X equals negative 102 divided by 37. Ooh. Is that lowest terms? But we covered a lot of ground here, and I want to make sure that before we wrap up this example, that we've again been able to talk strategy about this. So there were three important issues with this original problem that we wanted to fix. The first one is that there were fractions all over the place. And the sooner we can get rid of those, the better. So that was the first thing we did. Let's clear denominators. Find a common multiple of all the denominators that are there. So we used 15 in this example because our denominators were 3 and 5. And just multiply by 15. After all that multiplication dust settles, you're only going to have whole numbers left. And you've dealt with the fraction problem right out of the chute. Always a good decision. After that, we still have x's on both sides. We can fix the x on both sides problem by subtracting one of the x terms from both sides in a way that gets all the x's over to the left or over to the right. Depends, whichever way you want to do it. So we subtracted 12x to move all of our x's from the right to the left. And then we had x by itself on one side, but it still was wrapped in 2 layers of arithmetic. It was wrapped in a multiplication and a subtraction layer, and we used SADMEP, the reverse order of operations, to unwrap it.